So let's recall our expression once more for the Aharonov-Bohm function. In a similar spirit, let's use the contour integral representation for the Bessel function again. But this time there will be a crucial difference because our index of the Bessel function is no longer an integer number. So instead of a closed loop integral, we'll have a Hankel type contour in a complex plane. And the complex plane itself will have a branch. Will have a branch cut. So here our nu equals n minus alpha modulus. But again, since we are interested in the sum over this n, we will split our summation into two pieces. The first piece will run along the positive values of this index, and the second one along the negative axis. So let's actually see how this works. Well, first of all, we plug in this decomposition, this integral representation. Now let's split our alpha parameter, which in principle is any real number, into its integer and fractional part. And then we change the summation index from n minus integer part of alpha to n. As a result, the sum is split accordingly. Well, first of all, in the first sum, n will run from 0 to plus infinity, and an will change into an plus integer part of alpha, and the modulus sign can be dropped. And the second sum looks almost identical. Sorry, if I dropped actually additional factor I integer part of alpha theta. So the second part is as follows. And again, we can consider these two sums differently. First of all, what we notice is that both of these sums contain t in their denominator. Indeed, here in the first sum, it's almost obvious because we have these positive values of n. And the second sum, you see that n is negative, but here we have minus n, hence again. And we expect that both sums will converge for t greater than 1, which is quite crucial. It's our first self-consistency check, because we know that our contour, which is now a Hankel type contour, always contain, it comes from minus infinity, so it always contains these points with large values of t, with obviously when t is greater than 1. And if we were so unlucky to get the opposite condition, like in previous case, where in some sum t had to be smaller than 1, then we would have a problem. So, but fortunately, right now we don't have this problem. Right. So now we understand that somehow we should obtain, first of all, the incoming plane wave. That means that our integrand should have a pole at such a point that t minus 1 over t equals minus 2 I cosine theta. And there should be a simple pole, like in the previous case. This is a simple quadratic equation, and you can solve it for t. And once you've done this, you will get t equals to I plus minus theta minus pi by 2. So let's see. For example, we expect that somehow one of these sum will be turned into the following expression, like in the absence of scattering. So it's it should be something like 1 over t minus e to, for example, I theta minus pi by 2. And let's actually, for large values of t, for t greater, the modulus of t greater than 1, let's actually decompose this into a geometric sum. What we get is 1 over t, and the sum from 0 to plus infinity. And what we can do, we can actually multiply this sum by the corresponding exponential to obtain write that kind of expression. So it will simply be the same sum, but taking from 1 to plus infinity. And you see a direct correspondence. Here we have t in the denominator, like here, and we have e to I and theta in the numerator, precisely like here. So now we can identify these two expressions. So if we want to get something like a plane wave, we should assume that this kind of sum will converge to some kind of this expression up to some ordinary or arbitrary multiplicative constant. Now let's investigate the second root. The second root is with minus theta. Again, the same procedure. We perform the same thing. Obviously, we'll get very similar expression, but here we are interested in the sum which starts from n equal to 0, not like n equals to 1. So let's actually add here additional t factor, and this will simply gives us the sum from 1 to plus infinity, e to minus I theta minus I pi by 2 divided by t to n. From 0 to plus infinity. Right. So, and finally, we can change n to negative n. To get precisely our desired expression. So minus I theta will change to I theta. Right. And finally, we identify these two sums with their following expressions. So the first sum, let's call this sum like with symbol 1. And this is the sum from n equals 1 to plus infinity of a n plus integer part of alpha e to I and theta divided by t to n. And if everything is done correctly, then this sum should be equal to this expression up to multiplicative constant. So it's some kind of C1 constant times e to I theta minus I pi by 2 divided by the corresponding simple pole-like expression. And the second sum, which is here, should be identified with the second expression up to, again, some arbitrary multiplicative constant, which I denote here C2. And our final task is to fix these constants. Well, how are we going to fix them? Well, obviously, by the way, from these two equations, you can define all these constants, a n plus integer part of alpha, and consequently all these a n, and obtain the correct wave function for this Aharonov-Bohm effect, which is quite peculiar properties. But to fix this constant, we'll need to check the single valuedness of our function. For example, our psi function should coincide at values of theta equal to pi and minus pi. And this will be discussed on our next slide.